All right, welcome and thanks for joining, as always. So section 1.6, what we're going to be talking about here is inverse functions. So in this section, we're studying inverse functions. So when we're talking about inverse functions, we're talking about things that undo, and I did air quotes, you can't see it, but we're talking about things that undo other functions, sort of like addition and subtraction undo each other, multiplication, division. Now we're talking about entire functions that undo each other. So, formal definition, inverse function. A function is said to be an inverse function. So a function is said to be an inverse function, and this is going to be a relatively long definition. It's probably not enough space, so write small. An inverse function if, comma, if when the two functions are composed of each other, the result is the identity function. All right, so a lot that sort of goes into that. A function is said to be an inverse function if when the two functions are composed of each other. In section 1.5, we talked about composition. So that means if f of g of x and if g of f of x, the result should be the identity function. And the identity function is just y equals x. So what this is saying is two functions are inverses if when you substitute them into each other's variables, you get just plain old x as the result. So if f and g are inverses of each other, then f of g of x is equal to x, and g of f of x is equal to x. So again, the composition both ways has to give you the identity. And you need to make sure that you're checking both ways, not just one way. If g is an inverse of x, then what we can say is g of x is equal to f inverse of x. So when you see this little -1 here, this is read as f inverse x. It's not a power by any means. It's not like I'm raising this to the negative first power. It's just the way that we denote inverse. So if f of x is equal to x plus 4, then the inverse of f, inverse of f, is going to be equal to x minus 4. Your reasoning for that, and we'll talk about how to actually come up with these, but the reason that that's the inverse is because if I take x minus 4 and substitute it in for x, so I just replaced x with x minus 4, then I have a plus 4, I would get x. On the other hand, if I take x plus 4 and substitute it into this x, I'd still have a minus 4, and I'd be left with x. So since both of these gave me x, that I just did the composition, and we'll show it more formally later on, don't worry. But since both of those just gave us x, this is an inverse. All right, so some explaining to do. For one, I'll just maybe draw a little line here. These two things are not related. I don't want you looking at the function and thinking it goes with these values. They're not matching. So keep in mind the idea of domain and range. Domain, when we're talking about domain, we're talking about our x values. And range, we're talking about our y values. What happens when we start talking about inverses is those get flipped. So if you're looking at f, the domain of f is the same thing as the range of f inverse. And the range of f, the possible y values that I can get, is the same as the x values of the inverse. And you'll see this when we start actually solving inverses, which we'll do in this section later on. But what you see is that the way in which you solve for an inverse is that you literally switch your x and y values. So now if we look at this table, I have a table that's relating x to f of x, and I'm asked to fill out a table relating x to f inverse of x. And again, we just want to use this idea that what happens in an inverse is x and y just switch. So instead of being this coordinate -3, 4, it becomes 4, -3. Instead of -1, 1, it becomes 1, -1. 1, -2 becomes -2, 1. 3, -5 becomes -5, 3. And -8, 5. We're literally just switching x and y. All right, then graphs of inverse functions. If f and g are inverses of each other, then they are a reflection of each other over the identity function. So we have y equals x. That's our identity function. And what we're saying is that we should see a reflection over that line y equals x. So, if you want, and we will do this in class just to check it, but in your graphing calculator, feel free, just pause the video, go type in those two functions. In y1, type in 2x cubed minus 1. In y2, type in the cubic root of x plus 1 over 2. And when you get those graphs, what you're going to see is that they are symmetric over y equals x, which is a diagonal line. So it's not that symmetry that we're used to where we're talking about over the y-axis or x-axis. But that's what we're going to be looking for. And we'll talk about putting that in a calculator and all that fun stuff. All right, skipping ahead a little bit. The existence of an inverse. So it is possible that given a function, there is no inverse to that. So assuming you have a function, the function must be what is called one-to-one. And this right here, just saying the same thing, one-to-one. A one-to-one function means that each x is paired with only one y, and also each y is paired with only one x. So this extends the definition of a function. When we talked about what a function actually is, we said that every x value can have only one y value. Now what we're saying is, in addition, each y value can only have one x value. The way that we check this is what's called the horizontal line test. The horizontal line test works the exact same way as the vertical line test. The horizontal line test, all you're doing is drawing a horizontal line, and if it crosses the function more than one time, then it does not have an inverse. And we'll talk a little bit about that shortly. So algebraically, let's say I want to find an inverse. So earlier in the notes, I just said, hey, it's going to be x minus 4. But how do we actually find that? The first thing that we want to do is isolate f of x, if it's not already isolated. So isolate f of x and call it y. Next, we're going to switch x and y. And I mean that truthfully. You are just, instead of it saying y equals, you're putting x equals. And then for the x, you're switching it with y. Then, it sounds stupid, but you're going to then solve for y. So you just switched x and y so that you can solve for y. Once you do that, you switch y to f inverse of x. So I solve for that y, and now I call it f inverse x. And the last thing that you should do is verify. All right, we'll do these examples. Please really make sure that you go at least like skip ahead to these examples. Really cool, important stuff. So now, last and extremely important thing. What if a function fails the horizontal line test? So you can fail the horizontal line test, which means that there is no inverse, but sometimes we can fix that. What we are able to do sometimes is restrict the domain. And we're doing that so that it does pass the horizontal line test. So for example, if we had y equals x squared, just going to draw that really quickly. And I always mess up that graph, as you know. Y equals x squared is going to be a parabola. And you don't have to draw this next thing that I'm going to do, but if I were to draw a horizontal line right here, I can see that it fails the horizontal line test. So instead, what we're going to do is restrict this domain. If we change this function and say f of x is equal to x squared, but given that x is on the domain of 0 to infinity, what that means is this graph is starting at 0, and you only have the x values that are positive. So I can get rid of this piece of the parabola. And now if I were drawing that same horizontal line to do that horizontal line test, it would not fail the horizontal line test. And now I would have an inverse with the restricted domain. So f is now a one-to-one function, which means I can take an inverse of it. And that's exactly what we're going to do now. So what is f inverse of x? Well, f of x is equal to x squared. Again, that's given that x is on the domain 0 to infinity. And just a little preview of how we solve this. We switch this to y equals x squared, and then we're literally flipping the variables. It becomes x equals y squared, and we solve for y. So I'd square root on both sides. Remember that when you square root while solving, you get positive and negative. However, remember that the domain of our function becomes the range for our inverse. So this becomes now f inverse of x is equal to. And because our domain here is only positive, that means the range of our inverse can only be positive. So I would just have the positive square root of x. So just again, iterating that, because the domain of the function is only positive, the range of the inverse will be only positive. And graphically, what this then looks like, we want just the positive square root of x, and we know what that graph looks like. There's positive square root x. If we were to restrict our domain the other way, so if in our parabola on the previous slide, if we said we only wanted the left side of this parabola, we'd still have f of x is equal to x squared, but now we're talking about restricting it from negative infinity to 0. So going through the solving, we'll get the same thing, y equals plus or minus square root x. So f inverse of x is equal to, well here, the domain is only negative. So my range, my output, has to be only negatives. So now we're talking about the negative square root of x. This is actually a really tough concept. It's something that often is overlooked, but we have to try and get that down the best that we can. So now, looking at our inverse function is the square root function, but only the negative of it. Notice this is a reflection, throwing back all the way to 1.4. This is a reflection over the x-axis because I just changed my y values. So I took this piece and I reflected it down. All right, go through, write down if you have any questions, make sure that you ask them at the beginning of class tomorrow, and then go listen to the optional video if you want to see a little bit more practice, especially with some of that solving of inverses, things like that.